Hello everyone, welcome to this GD on quantum pseudo telepathy. Now we shall start.
Hello guys. I would like request everyone. This is basically just an interactive thing. So chats, mics, videos, whatever you all want to be on, just bring it on. Yeah, that's pretty much it. And yeah, I guess
Can just unmute
we start.
anytime. Yeah.
Yeah, disturb us anytime, speak in between, annoy the hell out of us. Anything is fine. Absolutely fine. And yeah, so I guess we'll just get started. And yeah, so Alok, want to begin?
Yeah. The first light, please. With the music.
All right, welcome people. This talk is on quantum pseudo telepathy. Quick show of hands, how many people thought this was clickbait? Because it feels like a pretty clickbaity name.
Well, when we decided the topic, I thought that it was a clickbait. So.
Yeah, you can search up everything we're going to tell you in this talk is legit. Yeah, so I guess like anyone has some expectations of what this topic might entail. Any one of you guys? Come on.
There is something about game theory, so I'm interested.
Yeah, apart from that, of this thing which was read in the, I don't know, description of the store.
Yeah.
Anyone bring up this like, yeah. And for people who expect this to be telepathy, it's not telepathy. The same.
I mean, of course, it's physics, so it's not.
Also, it's pseudo telepathy. And yeah, sorry to disappoint you guys. There's no witchcraft going on here.
But you like it,
much,
I'm pretty sure. I mean,
yeah, it's fun. It's pretty fun. So yeah. I guess so. Let's just get right into it.
Yeah. So first of all, like starting from the very scratch, as you promised, like PH 107 and MA 106 being the very basics. So first we introduce the Heisenberg's uncertainty principle. So it just states that the position and velocity of an object cannot be measured exactly at the same time, even in theory. Because like any attempt to measure precisely the velocity, so to say, of a subatomic particle of an electron will knock it out of in an unpredictable way. So, like simultaneous measurement not being possible. So don't be like, this is not off the topic. We'll just come back to a big discussion on HUP in a minute. So, yep, the next slide, please.
Yeah.
Yep, so the bang for the buck, I mean, the main thing. So what is the spooky action at a distance that Einstein are talking about? Like, so let's first of all, like introduce a few terms over here. So there are two things known as non-locality and realism in quantum physics. I mean, so what is quantum non-locality? So quantum non-locality basically refers to the phenomena by which if you measure the statistics of a multipartite quantum system, you do not admit an interpretation in terms of a local realistic theory. So that's a bit of jargon, let me say, but I'll just simplify it for you. So if you sort of measure a property of a particle, so it does not only affect the immediate surrounding of that particle, it can also affect so to say, a particle at a very vast distance, so to say light years apart, without being actually interacting with that particle. So that is quantum non-locality. That is essentially quantum mechanics is non-local. Everything is somehow connected. So that is quantum non-locality. And our famous Einstein, beloved, he did not believe in non-locality, I must say. I mean, he said that particles cannot interact with other particles that are very far apart. Yep, just a minute, I guess, technical issue. Yep, yeah, present to that. Sorry for that, people, but that's how this session is going to be, a more on like the on-site, the on-hands experience thing. So we're talking about the quantum non-locality, right? So quantum non-locality is essentially that the particle does not only affect the immediate surrounding of the particle, it can also affect other things that are at a very vast differences apart without actually interacting with them. And another thing being realism. Realism is the idea that the universe actually exists independent of your thought process. Like even if you don't think about a city, that city actually exists. So this was the idea debated by Niels Bohr. I mean, he said that universe does not exist when you do not think about it. So yeah, this might seem like a bit philosophical, but it's the thing. So any thoughts on realism? I mean, yeah, that like this is a big thing, that even if you're measuring a property of a particle, then it does not mean that if you would not measure that property at that instant of time, then that property would not only exist at that instant of time. Well, does it mean that? I mean, anyone? Very much like the peekaboo game that we had in our childhood.
Pranav, you
So
can't hear you.
Hello, yep.
Oh, I think Ronak was muted when he was speaking something.
Yes, I was. Okay. Yeah, the point is that like when you are the entire point when you measure a particular particle at velocity at 1 second and then at 2 seconds, you can't be sure that the velocity is constant between 1 and 2. And there's no possible way of being sure because you can't possibly check all infinitesimal elements of time and check whether the measurement is exactly the same. So how can we believe in realism? How can we say the subject exists without measurement? So yeah, what do you guys feel? What side of the universe you're on? Is it like a hologram? Is it um, is it like something that exists even without us measuring it, or does it just come into reality when we measure something?
I mean, how can we like assert that nature exists without the human mind? Because uh, if we ourselves don't exist, then we cannot verify the fact that nature exists without us. So it's a bit weird.
It's weird. I mean, also, how do we know the same? How do we know the nature we are talking about is the same kind of nature? Because yeah,
Also, I mean,
how
like,
do we know our minds work in the same
you
exact
exist.
manner?
So I mean, it does not mean that in the other room of your house in which you do not exist, I guess that does not, the room itself does not exist. I don't know. I mean,
Yeah,
I'm
but it
just
is
here for
about
the
it is about observing as well, right? If you didn't observe it, then did it actually happen, right? So I mean, you define your nature for yourself. I mean, if you get what I'm trying to say.
I was going to very like a code drama scenario. I didn't see it, so it doesn't exist. No proof, no evidence.
I mean, I'm not talking about whether it exists or not. I'm saying, how do you know whether it exists if you didn't observe it?
I mean, that's exactly the point. You don't, sort of. It's not that simple.
I mean, the problem is, how do you know? So also know like what is the existence of nature? I mean, like in what form the nature exists? Probably it does exist, but it is just a mixture of all the possibilities that into which it could exist.
And yeah, and also the fact that we take object permanence, which is like the presence that an object is there when we don't look at it, for granted. So like babies, like this meme really says on the left, the fact that you hide behind two hands and they don't assume you're behind those hands initially, right? That's how our brain develops. So when our brain is in a developing stage, we don't assume that the person could hide behind those hands. We just see those hands behind which a person is hiding. And we just get surprised when the person comes out of those hands. That's one possible example. The other possible example is just laughing at us being hysterical. But either way, the point is that we take that the reason that objects are there for granted. And this is not really a thing that we can assume in science, but we have all throughout history, we have assumed it, and we haven't really done a lot of like good work on proving it.
But the peekaboo game actually reminds me of the fact that like babies actually think that if you're not visible to them, then you might actually not exist. So, but that idea of permanence is so instilled into us by the time we actually like come to college, that if it would not have been that, like scientists are all actually planning to teach college entrance like the topic of physical permanence or quantum permanence, that like things do exist, proving it mathematically even when you do not see it, but like it is instilled into us that so that they do not need to do it now.
Yeah, one thing I would like to say here is that when we are talking about nature or when we are talking about object, basically what we are talking about is material. And if we look at material, the actual material present in the universe is less than 0.01%, right? And if we look at the atom, then actual material present in that is like, if you consider the atom to be a building, then the size of nucleus is, as I have heard, equal to the button of that lift in which you might go to the top floor. So what, even if you, let us say you studied all the matter in the universe, still what you have studied is just 0.01% of the universe, right? Rest of the universe is nothing else. So basically, if you really want to understand the universe, you have to like study where did that matter come from, or where will it go, and ultimately it is nothing, right? So
Right,
that is a point to be considered, right?
And the way you put it, it makes it so marvelous that we are able to like look at that 0.01% of the universe and make sense out of it. So, and yeah, in fact, we're talking about a very statistical improbability. We would rather say the universe is not made up of matter. And yeah, that's a big point.
But
Yeah,
like,
I mean, even
yeah,
yeah,
go on.
please go ahead.
No, go on. I'm fine. Coming
So,
back.
what I was
This
saying
is
is
fun.
like the example that you gave regarding, measurement of velocity of a particle, right? If you measure it right now at 1 second, or let us say at 2 seconds, it might remain the same because you are measuring the velocity, that is some kind of momentum. I mean, that will remain same. But the moment you measure the momentum, the uncertainty in position becomes infinite. And the moment you measure it, I mean, that once you do some measurement on momentum, that momentum is the state of that particle kind of falls into that eigen state of momentum. But uncertainty in position becomes infinite. And if you measure the position, the uncertainty in momentum becomes infinite. But what I am saying is, okay, you did all this, you developed quantum mechanics, everything. That's perfect. But ultimately, the measurement that you are going to do is just on some electron or maybe on some photon. It is only going to be a matter, right? And that, I mean, the force that is binding that electron to the nucleus is through some space which is neither matter nor nothing. It is nothing that is binding that force between these two. So ultimately, you have to study the magnetic field, electric field, and all those things which are existing in nothingness, right? You can say about, you can talk about electron, you can talk about proton, but there is one more thing. There is one more thing, that is electric field or magnetic field or gravitational field. So there is
If
like,
you think about in terms of energy, right? Fields also do have energy. Fields also do have momentum. So they may not really have like mass per se, but we relate to it in that manner because you have to consider it. You're absolutely right.
Yeah, so the point is that you can't study universe with matter, studying matter alone. You have to take into account the energy aspect of it as well. That will kind of make sense ultimately. And that energy can exist as in nothingness also. I mean, this whole universe. So we can, in a way, we can say that this whole universe is like 0.01% matter and just 99.99% energy. I mean, here what I'm doing is I'm quantifying that nothingness as energy itself.
Exactly.
But one never knows in these things, So that is my point.
That's true.
I mean, that does bring forward the fact that what do we actually consider observation as? Is it like actually seeing that this table exists in front of me or as observation, or like probably this has an effect in the reality? I mean, that is something for you to think about, I guess.
No, actually, I spent a considerable amount of time thinking about the same thing. I mean, all kind of like whether it is quantum mechanics or what. So the one idea that floats out there is that it is not the table that is existing. It is the existence that is appearing as table, right? So ultimately, existence is the more permanent thing, and that existence appearing as table, chair, or you or me or laptop is kind of consequence of that existence. I mean, it was an idea that is floating around somewhere. So
That's fair. It's like a completely valid idea that's been there since quite a few years. You're right.
How do you like prove existence? Like, okay, I can like, probably just say कि हाँ ठीक है exist तो कर रहा है, but you prove it by observation is, I don't know. I mean, I think unless you, how do you say something
yeah, actually,
exists?
then the question also arises: who do I have to prove it to? I mean, I have to prove it to
Okay,
you.
that is
You
that
are
I
is
mean,
yeah.
that
you
is
are also
Yeah.
made of matter, and you are also made of that particles and
Yeah.
everything. Your brain, what is brain? I know
that
there
is
is
a
something
valid
called
question,
as
I guess.
medulla. I know there is something called as cerebellum, but what is mind? That is also a question.
So
Yeah, that's a good point to make there.
yeah. So let's just get back to these crazy people who try to deal with this question and others. So yeah, let's just begin with one of the famous people and one of the most notoriously, like the most notorious person who didn't let other people's ideas actually stand. But we won't talk about that because because we respect him sort of. And Einstein. So he released this entire. He believed that the universe was real, that it actually existed between observations. He believed that it was local, which means that like information cannot be transferred as fast as the speed of light. And he believes that quantum mechanics is not complete because we don't understand it, like the wave function collapses. It exists as a superposition because there are certain hidden variables which we don't get. And therefore he gave an experiment and which we'll hear about in a bit to try and prove this to Bohr. And
Well, like Bohr was not a physicist. I mean, he had some weird, crazy, but like probably more realistic ideas, I guess. I mean, Bohr did believe in non-realism, but he did have somewhat a valid argument, I guess, because Bohr essentially believed that when you do not observe the matter as such, observe the universe as such, it just exists as a superposition, as a sort of a fuzzy mixture of all the possible states that the universe could be in. Well, that is what we believe in quantum mechanics, essentially superposition of all the probabilistic states. And then Bohr did believe in non-locality, unlike Einstein, I mean. So non-locality, as we have mentioned earlier, just states that every particle can, like a particle can affect on the particle which is miles apart, like vast distances apart, and not just its immediate surroundings. And Bohr did believe in another interesting thing, that Copenhagen interpretation. So Copenhagen interpretation states that essentially because of non-locality, like if two particles are connected, I mean, so there can be a common wave function that can define both the particles. So if you measure something for one particle, like probably its position, then it could collapse the whole wave function for both the particles. And then this could just affect the other particle badly. I mean, this could just affect the measurements for the other particle. And this is why we have believe in non-locality. That was the basic reasoning behind the non-locality, the Copenhagen interpretation from the Bohr.
right, and so this is basically a debate of the ages. But this is what Einstein sort of proposed, and he was like, he basically believed that Bohr was talking to truth. And he proposed this thing called the Einstein-Podolsky-Rosen paradox, the EPR paradox, which was like one of the biggest things which he ever tried to do. And he introduced the concept of quantum entanglement. And basically, he believed that if the particles are sort of interacting with each other and then go really, really far apart, you could measure both its position and its momentum at the same time. And if they would have, say, opposite spins, you would measure spin up and spin down of the particle at different intervals, and that way you could technically get over the Heisenberg uncertainty principle. But That's
I mean,
where,
this was the thing, like Einstein when just proposed entanglement, like this was just an idea that if suppose you wanted to measure the spin of two particles, two quantum entangled particles, that I must say, then you could just measure the spin of one particle, and you automatically know that the other particle is doing the opposite spin. So, but like here comes the idea that first of all we should explain what are quantum entangled particles. So we need to establish quantum entanglement between two particles. Like in the later stages, the scientists did do that experimentally by how he did it, that he just broke a photon into two different photons. And because the next two photons came from the same photon, they were entangled particles. So even if you make them go light years away and you measure the spin of one photon, then you automatically know the spin of the other photon. So that is essentially quantum entanglement. So you can actually know the information without the classical limits, like without traveling through the speed of light, you can just know the spin of that photon instantaneously. I mean, that's pretty awesome, I guess, quantum entanglement. And this also gave rise to those I mean, not so genius, I guess, probably now, but those ideas about communicating faster than the speed of light.
yeah, so Bohr still believe that this quantum entanglement was due to the fact that quantum mechanics is non-local in nature. And this kind of brings us to this person, Bell.
I mean, what did Bell do? Basically, see, Einstein ने क्या बोला? I mean, Einstein said that there are two particles or light years apart, but this is spooky action at a distance. So how does this actually happen that these two particles who are at a distance, you can measure the spin of one particle and you automatically do the spin of other particle? Like, what is behind the scenes of this thing? So Einstein proposed a theory that there's something called locally hidden variables that come into play. So, okay, so these are the variables that are hidden in the nature, in those particles, essentially, and we do not know them. So they store some kind of information. So if you suppose measure the spin of this particle and it comes up to be spin up, then you automatically know that locally hidden variables, the variables that were hidden in the other particle, they store and the information in somewhat a way that the spin would automatically be down. But there was a big flaw in this idea that if actually there exist locally hidden variables, so then that means that we cannot essentially determine the local hidden variable because we could not find anything physical near the particles. So if we cannot actually determine the locally hidden variables, then that means that quantum mechanics is incomplete. And that was a big flaw in the theory. So then later came Bell with Bell's theorem and Bell's inequalities, did some spooky experiments with physics and the random stuff, and then he just proved Einstein wrong. Like,
I mean, it was not really him. So what really happened is he proposed a version of the world which is local and hidden and developed certain inequalities from that. Then you had this person called Allen and other people who basically developed an experiment who measured the spin of photons, I mean, which is essentially their polarization, and faster than the speed of light, and were able to prove that in this scenario, then inequalities are not valid. Therefore, proving that quantum mechanics has a non-local nature. But it didn't really exactly prove that. It proved that quantum mechanics is not locally realistic, which means it's not local and realistic at the same time. So that means it could leave us three possibilities: that quantum mechanics is non-local, not realistic, local, not realistic, and realistic, non-local. Now, experiments were done to consider that mechanics is non-local a lot of times, and this has been, I mean, we believe it because we have a lot of experiments to prove that fact. So usually it's dealt with non-local, non-realistic, or non-local, realistic. And this is where the entire debate mostly lies. And yeah, so there's this other theme called, which people try and figure out, called Bohemian mechanics, which is basically the concept of point wave theory. So de Broglie, along with Bohemian, basically Bohm, actually, yeah, my bad, Bohm basically came up with the idea that it's a possibility that the wave could actually be pushing a particle, which is why sometimes you observe a wave and sometimes you observe a particle, which brings us back to wave-particle duality. And so they basically felt that there are no local hidden variables, but the entire wave has certain global hidden variables, which sort of guide the particle with certain probabilities. And they believe that this pushing of the particle is totally deterministic. However, this hasn't really been disproven, but it is not as famous as the non-local, non-realistic nature of Bell's theorem and Bohr's ideology. Because of this non-local, non-realistic table, we've been able to get quantum field theory. We've been able to integrate electricity and magnetism and the nuclear forces, even though gravity is still up for consideration, and also relativity. And we're able to integrate all of this with quantum mechanics, but we're not able to integrate that with Bohmian mechanics, and therefore that field is sort of, reliant upon improving. And for all you know, that might actually work because no one's disproved it yet. But we are more interested in, this is not why we're here, right? The reason why we're here is something completely different. We're trying to enter into quantum pseudo telepathy.
But first of all, people, do you actually see a very basic flaw in that pilot wave theory? I mean, I do want to hear it. Pilot wave theory essentially says that a wave is essentially just pushing a particle. I agree. I mean, I'm among the more conventional side that just believes that the world is realistic and non-local, which my friend does not. But let's keep that to a side. And so it does not being consistent, other than being consistent with general relativity and quantum field theory. There's another essential flaw in my opinion, in pilot wave theory. So for discussions, I guess.
Actually, sorry to interrupt you. Yeah, okay. So I was just saying the pilot wave theory is actually not exactly the same as the Bohmian mechanical theory. So in more specific, the pilot wave theory involves a driving term in the equation of the movement for the particle, which, as one is a wave essentially pushing it. And it's already been demonstrated in a fairly recent work. I mean, fairly recent in terms of I'd say maybe 2015, 16, 17 type, in which it was demonstrated that in fact, the pilot wave theory is false. And they simply just took an experimental example of it, where it's not able to even explain actually the double slit experiment of variation. So it is in fact wrong. But Bohmian mechanics is a little more subtle than that. It's not exactly speaking in terms of particles and waves. It's it reformulates everything and changes the measurement process essentially. So I'm not very sure if you can physically break it down as easily, but it's that is in fact the reason why it's Bohmian mechanics. Broglie was the guy not Broglie, but Brohi. I'm not sure how do the French people say it. They have their funny little pronunciation things, but so that's the reason why de Broglie's theory was in fact wrong, and Bohm said that I'm basing it off of that, but it's not exactly. But anyway, continue.
Yeah, we review for that insight of Bohm in many ways, because we're relying on you for that, not going to lie.
I mean, just say that it's realistic and non-local. I mean, it would be fine. People will accept it.
Yes. But apart, so now that we've cleared the air about all of this, you realize that it's really important to figure out and develop experiments on judging whether things are non-local, judging whether things are not realistic. And it's really important for us to realize which is the one we're looking for, right? So this is where it brings us to quantum pseudo-telepathy.
Yeah, so quantum pseudo-telepathy. So the big word that you all came for, I mean, the clickbait. So what is quantum pseudo-telepathy? So first of all, in certain Bayesian games with asymmetric information, essentially multiple players playing it for the same team, and all of them have some different information that they all need to share to actually win the game. They all have incomplete kind of information. So they have access to shared physical information in an entangled quantum state that can achieve high expected chaos and equilibrium. Big words, I mean. So essentially, for classical players to win that game, they can essentially make strategy before the game, that. So classical players, what would they do? they would actually go after a probabilistic model. They would go for an optimal probabilistic model that they are going to answer based on mathematical probabilities, and this is going to give them the highest possible chance of winning. But what if we play this game between two quantum players, between two players who share quantum entanglement? So because they share quantum entanglement, they can essentially, um, like transfer the asymmetric information. They can actually win the game with a very high probability rather than the classical players. So that is what quantum pseudo telepathy is all about. It is about playing a game that we are going to show you, a couple of those actually, between two entangled players who can share an entangled state between that information. So they have a very high probability of winning the game. That is like more than 90% or something. So that is very good. I mean, and yeah, it's just a theoretical experiment, and it basically proves the quantum non-locality. I mean, just want to put it out there.
It's basically, the point is like, after a few hitches, you could possibly make this into a real life experiment, especially with the advent of quantum computers. And this is done, it provides more experimental evidence that quantum mechanics is actually non-local. In fact, you could alter the experiment in such a way that you could actually prove that, hidden variables do not exist in quantum physics. And that is really a big thing we don't need right now. So now, this is all, so now you get why telepathy actually exists, right? Because entanglement, and one can give you a zero on the other end, etc., etc. So before you are ready to play a quantum pseudo telepathy game, we need to give you guys a quantum information crash course. Right? Now, the qubit essentially is basically a bit that exists in a superposition of ones and zeros. And yeah, and we don't really know what the exact superposition is around measuring. So I'll get into it right now. So this is the quantum diva, the qubit, which is a very finicky item, because it has to be really fault tolerant. Even a small change in energy can switch it to another energy state, and it's very hard to make these small items of information. And essentially, you can make it with about anything that has different energy states. So a trapped ion, neutral atom, quantum dots, impurity spin. So you'll have an up and down spin in phosphorus, donors, and silicon. And essentially anything with two energy states, and you have a qubit. And that's the entire point of the qubit. There's one more thing. You don't really have, you do need one more thing apart from the fact that it can represent two energy states. And that is, you need a way to create superposition. So if you have a way to represent two energy states, and you have a way of creating superposition of those two energy states, you basically have a qubit and the basics of all, quantum computing. Now, essentially, this is bracket. Or if you might make it into a karate chop and say bracket. But well, yeah. So zero is essentially, so now just give a representation of a bit of math. Zero and this weird right sign you see is the ket vector, which is essentially a column vector. And if the same thing is towards the left, it is a bra vector, which is essentially a row vector. So zero, so ket zero is the lower energy state, and ket one is the higher energy state. And the sigma is usually represented as a superposition of ket zero and ket one. And you have the summation of the squares. So because the probability of the particle existing or the qubit existing must be one, so alpha square plus beta square, which will be complex amplitude probabilities, also has to be one. And then you can write this entire thing as a alpha beta vector, column vector. So yeah, so essentially everything is sort of a qubit, because nothing is really fully something in this world, maybe even sexuality. But yeah, did you guys get it now? Any doubts or such? Because
I didn't understand how alpha and beta can both be complex. What would that physically represent?
Oh, okay, so
let's say both of them are 1 by root 2 iota. What is that representing? What the qubit is in what energy state? What is the iota representing there?
Okay, see, so the iota is technically just for math because when you are taking the actual probability of it, you take the mod square. So that's like the length of the complex vector. So it doesn't really matter in like when you're actually measuring the probabilities. But yeah, so it's basically for,
Right.
yeah. I mean, it does help with certain transformations, as you'll see in like, yeah, with one of the examples of the game, you see it does help in certain transformations.
So
Although,
what is
yeah,
psi? What is psi? Psi is exactly what? Is it the state? Is it like
the wave function. It's the wave function. Psi is a representation of the wave function.
right, right? Okay, got it, got it. PH
Like
107.
PH1, exactly. So yeah, that's just anyone else.
I think one way to look at is like size the state of particle, which could be either in lower energy state or higher energy state, right? So
Definitely,
basically,
definitely.
alpha square gives us the probability that it is in lower energy state, and beta square gives us the probability that it is in highest energy state. And actually, until unless we do any measurement, we assume that it is in both the state, right? So basically, that since alpha square is the probability being lower energy state and beta square is the probability of being higher energy state, and we know that there is a particle somewhere, so both of them has to add to one, right? For probability of finding a particle has to be somewhere. So that is like one another way of to look at it, and that is,
Yeah.
this is for the case of a single qubit, right? Because when we are talking about teleportation, we have to consider 2 qubit at a time, and then consider all the
More
possibilities.
obviously, it's just like the basics of the math that come to it, I guess. So yeah, you're absolutely right. That does make sense. You consider it as like the probability of being in those two states. So technically, that does work. And yeah, let's just go to the next part of this. Yep. Now, another thing, a small thing, which is like you have unitary matrices which sort of set up various superposition setup. So if you multiply the qubit with a U matrix, it sort of it basically multiplies the qubit with U00, U01, U10, U1, a matrix multiplication, and it gets transformed into a superposition of states in the following manner. And yeah, so it's essentially a mathematical representation of a gate of a quantum gate that converts those qubits into a superposition of energy states. And yeah, they're not pure energy states anymore. So you initialize it as pure energy states and then pure basis states, and then they get converted into a superposition state. This is the hammer transformation, which is kind of important to know. I'll be using this H in quite a few places. So it sort of takes the get zero and makes it, and basically splits the probability into a positive and a negative summation of 0 and 1. And it's equally it's an equal probability splitting because it's 1 by root 2. So yeah, that's essentially a hammer transformation, which will be important later on. Now, yeah, so anyone from the audience, now I explain what a qubit is. And again, its fault tolerance is so hard because again, you need 0 and 1's energy state, and you need to make sure that it doesn't go to the second one. So yeah, anyone, why do we not? So I have two questions. Let's start with the first one. Why are qubits much faster, right? Like it still represents a superposition. So why is it fast? Like you still have, I guess, a variable. You still have a probability of 0 and 1. So essentially it doesn't, like, how is it fast? Anyone from the audience? Right. Yes. Yeah. So anyone? So I guess the
I mean,
point
it's
here is
quantum
that
computer people, just chime in.
just
Anything.
Simon.
I mean, it's
I
quantum
mean,
physics. Anything is going to be right, I guess.
I really don't know. I mean, I thought about it, but I don't really see why they should be fast. I mean, they're wrong. They could be fast.
Okay, so essentially there are two things to note about this. The fact that so like when you're representing a superposition of a qubit, right? essentially alpha and beta are two variables in the qubit. So with each information, like in a computer, when you represented a bit, you could represent two states, a 0 or a 1. But when you're representing a qubit in a quantum computer, you're technically representing two states, so two numbers, alpha and beta, which will help you in your computation. So this sort of adds another, so it reduces the number of bits or information units that you need for communication, and therefore it sort of increases the time which you take to solve complex algorithms. However, we are really currently working on, the fact that measuring these and increasing the speed of the individual of, playing around with the quantum bit in the first place. Even though the number of units of data is less, we aren't really there as fast as we are with current computers because of fault tolerance issues, etc., etc. And in fact, we do have something known as a quintet, which is kind of a quantum bit, but it's got three states. So it's got 0, 1, and 2. And it's used in certain applications as well. So there you would have more numbers of representatives, 3 energy states, etc., etc. So yeah, that's pretty much basically it. So, and yeah, another slight math is basically when you have to measure the quantum bit and the probability. So let's say we are currently measuring it in terms of the basis vectors, which is 0, 1 and 1, 0. But let's say you had another basis of the H2 field, which is the Hilbert space, then you would measure the probability with this thing. Now, this basically represents the inner product of the bra phi vector and the ket B1 Bi vector. So when you take the inner product of them, you will get the probability directly. And that's just sweet math. And honestly, not that important. So this is basically what it does. And now we continue on to n bits. And similarly, you will have alpha 0, 0, alpha 0, 0, 1, all the way up till alpha 1, 1, 1. And this is for an 8-bit system with each individual probability squares summation adding up to 1. And this is the Kronecker. Now, there's something known as a Kronecker product, which is a tensor product. And it basically adds your, it basically multiplies in a certain manner, which is representative of outer multiplication. If you guys remember a bit of MnP 106. Yeah, so let's say alpha has alpha and beta, phi has alpha and beta, psi has alpha dash and beta dash, and then you multiply it in this particular manner to create a larger row matrix, a column matrix, my bad. So 0, Kronecker product of 0 is represented by the ket of 0, 0. So that's how we represent two final states. And finally, math, like quantum entanglement, right? So how do we represent quantum entanglement in math? So psi is, if it's a product of two ket vectors, it is a direct product state, because you can split up the wave function into two vectors. And if it's not a product, then it is an entangled state. So this is an example of 4 famous entanglement states of 2 qubits, and they're known as well entanglement states. And yeah, so that's pretty much done with the math. Now we can dive in, more or less. So yeah, so what does it mean to share an EPR pair right now, right? So if now let's say you have 4 qubits. So now let's say, yeah, Alice has the first and third qubit, Bob has the second and fourth qubit. Now, so that's a representative of, so basically Alice has a entanglement of the first and third qubit. Bob has an entanglement of the second and the fourth qubit, and their combined state is represented by taking the Kronecker product between the both of them. Now, so usually this is what it means to share an EPR pair. It's basically a common wave function to represent both your qubits, essentially written in math this way. And you have 2 qubits and they can't interact with each other faster than the speed of light. I mean, it can interact with each other faster than the speed of light. So yeah, now let's come to the first quantum game, or pseudo telepathy game. And yeah, this is where we are going to dive right into, like, we're actually going to like develop experiments to prove non-locality. So this is called the Greenberg-Horn-Zellinger game. Everything comes in threes, honestly. Also, though, Mervyn did some work here. He's basically the guy who made a lot of these games into into the quantum pseudo telepathy format, which is what and prove a lot of these things related to what we're talking today. And Greenberg, Holmes, Zellinger were just the people who proposed the game. And the entanglement state is known as the GFC state, which will, yeah. So now let's do a brain exercise, right? So this is a simple game, and the game is a 3-player game. Okay, threes. Kind of exhausted already. Each person is asked 0 or 1. So can I have 3 volunteers from the audience in case anyone? Guys, 3 people. Come on.
Okay, I'm in.
All right. Hello,
I'm
Roshni.
in too.
And who else?
Can I be your third person?
Sure. Right. So now let's go. So basically, person Palak, Roshni, and Shweta will be asked 1 question each, 0, 1, and so basically we'll ask you a 0 or 1. We'll tell you, but I'll tell you whether your question is 0 or 1. Now, suppose you 3 can't interact with each other, right? And you're supposed to win this game, but first you need to understand what the game, how do you win the game, right? So I will ask you one of 4 questions. The 4 questions are possibly so basically I will ensure that the parity or the mod 2 sum of my 3 questions given to you guys will be 0. So I won't so you'll have 2 ones or no ones at all when the 3 questions are asked you guys, and your answers have to be equal to the sum. The parity is equal to the sum is equal to the parity of the sum of x plus y plus z divided by 2. All right, follow me. So let's say 0 plus 0 plus 0 divided by 2 is 0. So your answer in this case should have been 0. In case of 1 plus 1 plus 0, your answer should have been 2 divided by 2 is 1. So your answer's parity has to be 1. Your answer's parity is 0. But what do you mean by answer's parity? I would take the sum of all 3 of your answers, whether it's 0 or 1, and then decide whether you're 1 or not. Now, let's say we did the game classically, right? Let's say you can't share an entanglement pair because you don't have access to a quantum computer, sadly. So, guys, what would be the classical strategy or the most optimum classical strategy you could possibly make in such state? In what way you would try to win the game at all points of time? What could you possibly do? You can use random probability distributions. You can toss coins, whatever you guys want. Shweta, Palak, and Roshni. What would you do?
So you want the 3 of us to
Develop a
what
strategy,
right?
yes. Yeah, so I will be asking each of you all individual questions. I can type it in the chat, in fact, and which will be a 0 or 1, and you'll have to individually reply a 0 or 1. And then you have to ensure that the parity of your answer is equal to the parity of the sum of x plus y plus z divided by 2.
I mean, classically, you'd say, okay, I'll just say 1 because there are 3 outcomes where the parity would be 1, whereas there's 1 where it's 0.
Yeah. I mean, yeah, but if you had to individually decide who would say 1 and who would say 0, how to go about doing that? I mean, it's you 3 give separate answers, right? So each person has to give a 1 or a 0. So yeah, that essentially you need to try and write a 1 because the answers are 1.
One way of thinking of it is that if all of us do give an answer of 0, we are guaranteed that the parity would be 0 too, right? We don't really have to think, but it would involve, obviously, telepathy between the 3 of us in that case.
I mean, it wouldn't, because if you do say 0, but that answer is only right 25% times.
And you could just develop an optimal strategy to win the most probable answer, like most probably you win.
Yeah. I mean, no,
What
she
could be
is
the
right.
most probable
Right.
optimist, like optimal model? Probably something like, I don't know, give a hint or something.
I mean, so essentially, Roshni is right because you need to aim for those 3 ones there because you would rather, or just give the answer as 1 and then, your output would be 1 and therefore you would, like probabilistically speaking, get the answer right 3/4 of the times, and that is a really good method. But any other way of like improving upon this classical like outcome, like any way of like better it.
What if I want 1, 0, and 1? Wouldn't that guarantee a 1 in the end?
1, 0, and 1. So you're saying each individual person says, the first person says 1, the second person says 0, and the third person says 1, right?
Right.
So that would give you a parity of 0 in your output. So that would only be so 1 plus 1, 0. So it give you a parity of 0 in your answer, so it will only be valid 25% times.
No, an answer of 1, 0, 1 will give a parity of 1. Right? I mean, 1 plus 1, 2 by 1, 2, 1.
Exactly what I'm wondering. Wouldn't it?
I didn't get
I mean, that would be the classically most optimal choice. Like if you just assign 1, 0, and 1. That 1 plus 1, 1, and 2, 1, 2 by 2, 1. So that would give you a parity.
It's coming back to the fact that, yeah, so basically in this particular problem, you cannot make an optimal strategy better than 75% of the times. In fact, if you would just randomly allot any configuration to XYZ, say, which has a parity of 1 in the output, say 1, 1, 1, or 0, 0, 1, 1, 0, 0, or 0, 1, 0, all of them would equally have like a probability of winning at 75%. And you can prove this to be like the optimum classical strategy. So, in fact, first you prove that there is no deterministic classical strategy. So, yeah, so if you look at the inputs at the side of the inputs and you add them up and take their parity, you would see that the parity is even. So there's a 0 parity, but on the parity, when you sum them up on the side, you have parity odd. So you can't really have a classical deterministic strategy over it. And yeah, so we'll have to delve into like game theory, terminology over here. And even though we live in a free world and it doesn't really help that, we have to deal with such horrible definitions of probabilities, but we really do, because we do not have freedom. No one really does. So the omega of G for any game is basically the maximum successful probability over all possible probabilistic strategies. And omega tilde of G is the maximum success proportion, which is defined as the number of, so X and Y belonging to P. P is basically the question set. W is the winning set. And the number of elements of P such that W is basically and upon the number of elements of P. So the maximum, so F and G are basically two functions that we decide. So omega tilde of G is basically the maximum output you could get when F and G are, the most optimal answer functions. And this way, because P, the X and Y answers may not be evenly distributed, and you might have more proportion towards the more correct ones. Like, let's say in the previous example, you would not, let's say if you don't get the 0, 0, 0 state, like in your entire gameplay of 5 chances, it's possible because the chance of getting that question is again 1/4. Then you could say that omega of G is always less than equal to omega tilde of G. And because of that, we can prove that, see, omega tilde of G, the maximum success proportion, is always going to be less than number of elements in P minus 1 upon number of elements in P. This is because you have to have an integral element over here, because you would definitely have to, you can't really have a game where you don't win and win at the same time. So you would, if there is no classically deterministic strategy, omega tilde of g has to be less than or equal to number of elements of p minus 1 upon number of elements of p, which is 3 by 4 in this case, because number of elements of p is 4. And that's how we see that the 75% is the best optimal strategy you're getting in this scenario. So yeah, pretty much that. So any ideas on how can we communicate? Now, let's say we know that one idea happens 25% where we need a zero parity, and there's a 75% chance that we need an odd parity in the answer. So how do you communicate this using an entangled state? Any ideas, people?
I mean, just probably think about the qubits, I guess, that we just talking about.
Yeah, so we could possibly align one qubit to each person. Let's say Shweta, Palak, and Roshni will get one single qubit. And if they have an entangled state, maybe you could somehow increase probabilities when one, like someone gets a 1 or a 0.
You just make an entangled state and just use qubits and all the hints that we have given you just a couple of steps before.
So any ideas from anyone else? So yeah, so we basically we basically do have an entangled state, which is we call this the GSZ entangled state because it's the bra 0, 0, 0 plus the ket 0, 0 plus the ket 1, 1 by root 2. The probability of ket 3 zeros of ket and 3 ones as basically half. And this is the quantum victory strategy that we employ. So let's say each person has this function because iota, right? See, like there's an advantage of using complex numbers in the amplitude. That's not the main reason, but it's just an advantage. So let's say you're able to represent parity with the help of complex. So let's say the players share a 3-qubit entanglement, and 1 qubit is with each person. Now each person sees the question asked to them. So if it's xi is 0 or 1, and applies the following unitary transformation on their qubit. So if the qubit is x, so basically what you do is if the qubit xi is 1, you multiply it with I, and if the xi is 0, you let the qubit be. And essentially it comes out that after you apply this on this conditional basis, you get a state that when summation of xi is 0, you get the positive summation of 1 by root 2 plus 0, 0, 0 plus 1, 1. And if the summation of xi is 2, so you get 0, 0, 0 and minus 1, 1, 1. So you see over here, already splitting up the two cases in the, so this is the 25% probability case, and this is the 75% probability case. And now you can apply the H transform, the Walsh-Hadamard transform. And this really brings out the final solution. So if you have, let's say, xi 0, you're going to have to give an answer whose parity is 0. So you would basically have these 4 options. And while measuring it, one of these 4 options would come to life. And any one of these 4 options would give the right answer. So you could independently measure it and still get the right answer. And 0, 0, 1, and then 0, 1, 0, 1, 0, 0, 1, 1, 1 are all odd parity answers. So you would measure it and the parity would just appear. So you could measure it independently, and irrespective of which basis state it submerges to, it will still work. And this is the way you get a quantum victory and you always win the game, which is marvelous because now we have an experiment. So if you could actually set up a quantum computer, which is like, I mean, this is such a distinct apart, it's faster than the speed of light, and you could ask them independent questions. And, you could, each single qubit could transfer some amount of their own qubit. And let's say the 3 qubits have an entangled state. And if you could prove it sufficiently because you would have a difference of 75% to 100%, you would say that if you almost always win, then I'm saying almost always because there can be errors in your measurement. If you almost always win, that means the quantum world is essentially non-local, and this is kind of a nice, elegant way to show everyone that quantum non-locality is actually something that happens in real life, and it's not related to two photons banging into each other and measure to opposite ends after after faster than light or something of that sort. And it also shows you how you can sort of how computation becomes so much easier and so much more reliable and I mean, not reliable, but it definitely becomes easier and faster with these entangled states. You do things which you haven't done before. You can sort of establish if conditions in the bits, which is essentially what you're doing. And yeah, so this is mind blowing because if it is implemented properly, this is one of the advantages that quantum computing is bringing us. And so this brings us to the anyone with any doubts now? Yeah. So there is one more game. It's the Magic Square game. So yeah. So this was thankfully an Indian person who made this, and it's a 3x3 matrix with entries as either 0 or 1. And person A has to enter the elements into an arbitrary row. So the game master will sort of just tell person A that you need to enter elements into row X, and will tell person B that you need to enter elements into column Y. So now person A and B can't interact with each other, and they would win if the parity of each row of the row that A types out has to be even, and the parity of the row that B types out had to be odd, and of the column that B types out has to be odd. And also when the row and column intersect, they need to have the same number. So Merman did some work here. Again, he did help with the magic square. He's literally everywhere in quantum pseudo telepathy. So any ideas about the classical strategy you have, people? What is the best classical strategy you could probably adopt of it? And can you make this square in the first place? Let's say you had a square with which you had to fill with these rows and columns. Could it be made? Yeah, so essentially, what's happening here is this magic square this not really cannot really work in the classical world. You cannot have a square whose all row parities of all rows are even, parities of all columns are odd, and the intersections have the same number. It's classically impossible. But however, each individual row and column has, so let's say you fill in this magical square, out of 8 out of 9 places you will be able to, or 8 out of 9 configurations of rows and columns, you will be able to maintain the parity of even and odd respectively. And therefore the maximum successful probability is 8 out of 9 in this scenario. And the classical words doesn't meet our expectations, right? Again. And this is basically, yeah, it. And so again, we enter into the quantum thing and we try to use an entanglement of qubits. So any ideas on how we would entangle qubits for this? You've seen one example before. So this could sort of give us an idea of how to represent qubits. So any ideas, people?
I mean, it's very similar to the previous game. Just think of more inputs, I guess.
Yeah, so okay, how many inputs would we need? How many quantum entanglement pairs would we need? How many qubits do we actually need to solve this one? I guess that's a nice place to start with. So I guess we need to sort of so we have to get, I guess, 4 outputs from this thing. Because essentially any combination of row and column would have 5 elements, right? And if these have 5 elements, you would have to have 4 elements here, because the last element of the row A and B chooses will sort of be predetermined by the roots, right? You would have parity of odd, and I mean, you have even parity in the rows, and and an odd parity in the columns, and the intersection would have the same number. So you sort of need to just get 4 elements, 2 for A and 2 for B, that they need to write down in the magic square, and the 5th element will come on its own. So you need a qubit with 4 states. Now, I mean, you need 4 qubits because you need 4 outputs, and this really works. Now we come back to the entire, so you have to try and get the entire, now what we could possibly do, right? Now, you actually tend to back calculate this. Let's say you need, like, these are the possible outcomes I need, like, you identify each X, you identify each Y, and then you see that this is the possible quantum states which are okay and which will allow Alice and Bob to give final answers, and then you back calculate the matrices of each individual quantum state. But thankfully, we don't need to do that. It's already done by, for the magic square people, like Mervyn and the other dudes. And the first 2 qubits essentially are with Alice, and the 3rd and 4th are with Bob. So upon receiving row number X and column number Y, Alice and Bob do some matrix transformations. And so Alice then applies AX depending upon the row she got, and Bob applies BY depending upon his row column. And accordingly, they transfer into really nice outcomes. So essentially, when you have X equal to 2 and Y equal to 3, after Alice and Bob apply A2 and B3, this evaluates into this entangled state of 8 possible scenarios. And each person completes the row and columns with their parity, which is required. And again, any one of these 8 solutions, when they come out, you get a nice answer, and and it works. All 8 of these solutions work. So this kind of makes it, again, so 8 is to 9 to the first probability. So this sort of makes it a nice again, another idea why quantum computing is amazing, and another experiment about locality and non-locality, whether it does work or not. So we come to the uses of quantum pseudo telepathy, and this is basically, so it's quantum complexity and a communication exercise. Maybe because you have an entangled state, you could possibly set up quantum cryptography. Now, because you essentially have private and public keys sort of set up in a certain manner, and like you would have qubits, and one qubit can interact with each other. So you do a unitary transform to one of your qubits, and that would, be your private key. The unitary transform is essentially your private keys to public key. So those individual transforms are something which we could possibly use as cryptographic encoding functions. And it could also be the first loophole-free demonstration that the world can be local realistic. So as we saw that, Bell's inequalities were violated, but that only proved that the world cannot be local and realistic at the same time. This sort of can be modeled in a certain way that, everything is nice, and like everything you can test local and realism separately, as well as the presence of hidden variables separately. Now, there are a few issues with quantum pseudo telepathy that needs to be solved before everything can be done. So, anyone's heard about the Laplace's demon? It's this very creepy looking dude in the corner, sitting with like black material flying out of it. So it kind of looks like Slender Man. Yeah. Anyone heard of Laplace's demon? All right. So it's the concept that whenever you have anything deterministic, whenever like the universe is deterministic, and it just has a numerous amount of variables, right? So if you had the computational power or the mind to actually identify all these variables and realize how they interact with each other, you would probably control the universe and you'd be God. You know everything that's about to happen and everything that's already happened. And that is the concept of Laplace's demon, because Laplace believed that there would be a very unfair advantage for the person who is dealing with the world. And this is kind of where the entire thing goes berserk. Because if A and B, that's Alice and Bob, could communicate with each other, did they already know X and Y's questions in the first place? This is a very far-fetched philosophical experiment and just a thought experiment. It's probably not realistically going to happen. Or like quantum particles are all-knowing beings, maybe. That is one alternative to the experiment is not ruled out, right? No one's disproved that. So we can just keep it all open for this point. And yeah, so you also, the issue with this also is going to be that when light is going to hit at the same point, and you have like, you have to measure the answers of A and B at the same exact time, faster than the speed of light over that huge distance. So that's going to be an issue to get those answers to those questions simultaneously. And basically, also X and Y can't prepare their answers from beforehand to try and avoid any sort of interaction that might exist or quantum entanglement that might exist in the questions in the first place. And also currently we have imperfect detectors and fault tolerance errors, etc., which means that if we do measure, like if we get one error in say classical in a quantum pseudo telepathy game, and we can't say that non-locality doesn't exist anymore because our detectors aren't that great. So we would have to probably go that the quantum strategy gives us a probabilistically greater advantage, but we can't really say for sure at any point of time. So this is kind of the issues we have to solve with quantum pseudo telepathy before it can actually be implemented as an experiment. And yeah, any other issues that people can think of, because this is pretty random and it seems absurd. Like, why would you honestly apply this to games that there's just parity and creating parity concepts with bits and qubits? So conditional qubit parity, as I like to look at it. And yeah, these are not just it. Like, there are quite a few issues with this. So anyone, any suggestions on how we could possibly deal with quantum pseudo telepathy?
Wait, what exactly quantum what you said at the end?
Pseudo telepathy.
Quantum telepathy, right.
So
Yeah, no, I have nothing to say.
so, I mean, this is just an experiment for non-locality with you. So again, apart from, I think one possible thing would be to find the game such that the classical and the quantum probability are widely different, right? Right now we've looked at examples with 8x9 and 1, like 75% and 1. I mean, we should just try to increase that gap to create games such that the gap increases drastically. So in that way, we could possibly be more sure of our answers. And yeah, so that's pretty much it. Yeah, thank you guys.